So today what we're going to do is look at these cubic equations of state and then um, show you how to use the Excel solver subroutine and also the MathCad solve built-in functions to allow you to calculate the molar volumes. Usually pressure and temperature, as we've mentioned, are easier to measure, and it's usually the volume that we want to calculate. And of course, these equations of state are cubic in volume, so that makes them somewhat difficult to solve for. Just to review the general phase behavior of a pure fluid, we've got here a pressure volume diagram, PV diagram. This line right here is the liquid vapor equilibrium line. And so we've got liquid underneath and we've got vapor around. And then what I've drawn here are some isotherms. So this is an isotherm for a temperature that's less than the critical temperature. And the cubic equation of state is forced to be a continuous function, and so it's going to have this odd behavior like this. Remember, for a real cubic equation, or for a real fluid, the equation of state is just going to be a straight line, what I believe what you'll call in the second semester a tie line. You might use a term like that in your equilibrium separations class or your unit ops lab when you study distillation. But this will, this going down and then back up and then down again, that is purely mathematical. This has nothing to do with reality. But we accept that because the cubic equation of state does a pretty good job of modeling the behavior in this region. It does a pretty good job of estimating what the liquid volume will be and what the saturated vapor volume will be. And then it does a pretty good job of modeling the behavior after once we reach vapor volumes, pure single vapor volumes out here. So that's the isotherm for temperature less than critical temperature. And then once we reach above critical temperature, we just have vapor. And so we have the isotherms that are just about parallel to each other. If we were to draw an isotherm at the critical temperature, that isotherm would come down. It would hit the critical point in just one point. That's not a very good drawing of this representation, but it would hit that there and give us a isotherm that looks like this. Now, because it's a cubic in volume, it's going to have three roots. If we are in the single phase region, we still have three roots, but only one of those roots, one of those solutions for volume is going to be a real number. The other two roots for the equation are going to be imaginary numbers, and in chemical engineering, we don't ever deal with imaginary numbers. We throw those out. If we have a temperature less than the critical temperature, we can have three real roots. And so our roots, the first root will be the saturated volume. The second root will be this value right here, which is some intermediate volume. And then the third root will be the saturated vapor volume. So this will be the higher, this will be the lower. The middle root to this equation has no physical meaning whatsoever. And so it can be tossed out. So that's something you need to be aware of when you are setting up equations, you're setting up algorithms to solve for the volume. You've got three possible roots. It could be that two of the roots are imaginary, so you need to tell your algorithm, don't search for the imaginary roots. There's no need to, just search for the one real root. If you've got temperature less than a critical temperature, you need to know that you could have three roots. And so you need to be able to start your search algorithm so that you converge on a liquid root, and then you also converge on a vapor root. This medium-sized root is no good. It has no physical meaning whatsoever. It's the wrong answer. And so that's important depending on what your search algorithm is. You may have learned some simple ones like Newton's method and things like that. Using something like that is going to depend on where you start. So you have to have a good guess make sure that you start at the right place. Make sure you know where you're starting. Don't just pick some random number, because you have no idea if that number is here. You have no idea if that number is here. And you're going to waste a lot of time trying to figure out, well, did the solution that it calculate, did it give me the saturated liquid root, the saturated vapor root, or is it some physically meaningless root? So that's a little preamble for dealing with these cubic equations. Now let's look at an example, and this is an example from your textbook. I forget which problem this is, but we will, there's a problem in the back of your textbook that asks you to solve for the molar volumes for a number of components at a number of different conditions. And here we're looking at butane. The temperature that we're dealing with is 350 Kelvin. The pressure is 9.4573 bar. We want to calculate the molar volume of butane at these conditions. And so this top row, one of the things you'll learn when you're doing spreadsheets, once you figure out what you're doing, you're going to spend most of your time formatting. That's just the nature of dealing with Excel. But I've got my gas constant, ideal gas constant, and then I've got my other physical properties that I look up in either my textbook or some convenient source that I have from online. I showed you a couple different sources last time. These are the critical constants, TC, PC, omega, ZC, and VC. Excel does not do your units for you automatically. You have to control your units, so make sure that you're aware of what units you're using. I've got here the Antoine equation constants. Remember, this enables us to calculate the saturation pressure. And so I've got this here. You can see our saturation pressure is a little higher than the saturation pressure. This is just extra information. You don't really need it for this part, but later on in the semester you might want to come back to it. And then now what we're dealing with is a Redlich-Kwong equation. I personally don't like the Redlich-Kwong equation because I think it's the generalized correlation is just a lot easier to use. The Redlich-Kwong equation makes you do a lot more calculations, and you can see that from here. Remember, with the generalized correlation, all we have to do is calculate PR and TR. But with the Redlich-Kwong equation, we have to calculate, or we're given these extra terms here. And so you can look them up in your book and get these values. These are given to you. The formulas for these equations, or the constants, are given to you in your textbook. Again, just make sure that you're very careful with the units. Make sure your units are consistent and that you add in all the unit conversions as needed. So this is just setting the problem up. All right. So conditions, the critical constants for my component here, and then the Redlich-Kwong equations, constants. These are only based on this information right here. The properties, the conditions, and the critical constants. That's how these are calculated. Now, what I've done here is I've shown you what I've got right here is there's a couple different ways to solve this cubic equation, and one of the old-fashioned ways of doing it would be through do an iterative process. So what an iterative process says is, all right, let's guess a value for my volume. I'll calculate a new value for my volume. I'll then see what the difference is, and then I will update my guess for that volume and then go through it over and over and over again. And what I'm doing is I'm looking at, you can see it's about a 2.9% change, and that percent change from one iteration to the next gradually gets smaller and smaller until it reaches some threshold where I say, okay, I no longer have to do any more iterations. So that's what we have here, and we can do that for the saturated liquid. We can do that for the saturated vapor volumes. And so what I've done is for the saturated vapor, I say, okay, let's assume first it's an ideal gas. That's a good assumption. That means that we are going, hopefully we're going to converge on the vapor volume. We know we're going to converge on the vapor volume. We aren't going to guess going to set our initial condition to ideal gas and end up converging on the liquid volume, or the meaningless central root volume. So that's what we've done. The ideal gas, Z is equal to 1. I just plug Z is equal to PV over RT, solve for V. This is my first guess for the molar volume of saturated vapor. I then use this is the Z value for the Redlich-Kwong equation, and you can figure out how to set that up. And then I calculate, that's my next value of Z. So my Z goes from 1 to 0.86. What that is saying is that my next guess for the volume is about 86% of what my ideal gas volume would be. Physically, that makes sense because molar volumes are almost always smaller than what the ideal gas volumes for vapors are. And so that first iteration had about a 2.9% difference. I then used this as my next value for, or I use this as my next value, my next guess for Z. I go through and you can see here after 15 iterations, I'm converging on something that isn't changing for 6 decimal places plus 5 places to the right. So that's what, 10, 11 significant digits, about 10 significant digits. I'm not seeing any change. That's good enough. All right. And so my molar vapor volume using an iterative method is 2555. I can do the same thing for a saturated liquid volume. And what's a good guess for a saturated liquid volume to start with? What is cell T6? T6 is the beta value, and you'll find that in your textbook. Z, the compressibility for a saturated liquid, is a good guess is your value of beta that you calculate for the Redlich-Kwong. I do that. My first guess for the saturated liquid volume ends up being 80.66 centimeters cubed per mole. You can see that once I do my next iteration, that's a pretty big error. And you can see that it is difficult, or it is a slower converging process. And that makes sense if you go back to the slope here. It's a slower converging process here than it is for here because the slopes are different. All right. And so the converging process, you can see here, 15 iterations, I've still got some error. Finally, I could have probably taken this out to 30 or 40 if I really wanted to. It really doesn't matter. But I finally come up with a molar volume of about 133 centimeters cubed per mole. Doing things by iteration like this is perfectly fine. It's just kind of a cumbersome way to do things. So the easier way to do things would be to use the solver function in Excel. And so to get the solver function, I've already got a tutorial for that for you. Make sure you have I posted that at the beginning of the semester. Make sure you activate the solver function. You'll see here when I have the data menu item selected, solver shows up here. So go ahead and do that. How do I set up the solver function for a cubic equation? Well, what I have here is I have my initial pressure, and then I have the right-hand side of the Redlich-Kwong equation that is entered in equation form. And so what that is this is my equation form. If I press F2, my initial guess for volume is given right here in this cell. So this cell is B60. All right, so B60 is my initial guess for volume. And so if you look at that formula, you'll see that that corresponds to the Redlich-Kwong equation of state with all the other parameters and constants that are involved in there. So this will be my first guess. All right, and so if I put in 3,000, that's my first guess. All right, this is the pressure. All right, this is the pressure that I specified. All right, temperature is embedded in the Redlich-Kwong equation. All right. This is my first guess of my first calculated value of the Redlich-Kwong pressure, all right, with this volume. So what I have here is I have the actual pressure and then the calculated pressure from the Redlich-Kwong equation. What I want to do is I want to minimize the difference of these two values. This is my actual, this is my calculated from the equation of state. I want to minimize the difference, and I don't want to just minimize the difference because the difference can be positive or negative, right? And so a good way to ensure that the difference is always positive is I want to minimize the difference squared. So that way, if I'm overshooting or undershooting, my difference value that is calculated is always going to be positive. So that's why I have difference squared. And we did the same thing when we were doing curve fitting in that first tutorial using Excel Solver. So that's what we set up. I set it, this is my initial guess. This is my actual pressure. This is the pressure that is going to be calculated by the Redlich-Kwong equation. And then my difference is simply this minus this quantity squared. I suppose if I wanted to, I could have put an absolute value and just do the difference there. But usually in when we use these solver functions, we use the squared difference, sum of squared difference for these functions. So now that I've got everything, so I'm just guessing. If I really were smart, I would guess the ideal gas equation of state, which is, let's put that in, that is 3076. So let's put that in, 3076. All right, and you can see we've got a difference here. So let's click on Solver. My objective is B64. B64 is this difference squared. And what do I want to do? I want to minimize it. I don't want to make it equal to 0 because chances are that will never converge. So I click on B64, the difference squared, minimize it, and I'm going to do that by changing which variable cells. Well, the variable cell is B60, which is the volume here. So, oops, let me make sure that's B64, and this is B60. All right, and you can look through this, the stuff about this. The GRG nonlinear is fine. So I click on Solve. Whoops. Oh, I've got a typo there. So I click on that, and Solver has converged to the current solution. All constraints are satisfied. It says down here the solver has performed 5 iterations for which the objective did not change significantly. Try a smaller convergence setting or a different starting point. This would be if we thought there were problems. You can look and delve more deeply into this, but in this case, we're going to keep the solver solution. And what that does is that puts the solution in our B60 cell. So I say OK. And this is my ideal gas, or sorry, this is my saturated vapor volume. And so I've set that equal to, so I can say equal to that if I want, or something like that, or just copy and paste. So 2555.32, what do we get with our iteration? Iteration, we got essentially the same thing. All right. Now for the liquid. For the liquid, we just do the same, a similar process. I'm going to guess a value for V, and so I get that from beta and from Z, and so we did that calculation here, so that's 80.66. Let's put in 80.66. All right. Notice we've got a huge difference here. So what do? This is our pressure. This is our actual pressure. This is our calculated pressure. And then we need to minimize this, so I'm going to click on Solver again. Same thing. Click on that. We converged. Okay. And notice we get a, whoops, I should have, let's just leave that there. What do we get here? We get 56. That's not the right root. What happened? Let's try 86. We get a value of 388. Turns out 388 is the middle root. So what do we need to do? Let's guess a value of 50. 56. This is where solver is a little, in these cubic equations of state, are difficult to work with. All right, so now we get a value that makes sense. We get a value of 133 centimeters cubed per mole. This is why solving these equations like this is not the best, and you kind of have to know what you're looking for before you calculate it. The 56 value just did not make any sense. I'm not sure why that showed up like it did. I could probably go into the solver function and change some of the settings, but the correct value should be about 133.27. You can see that's what we got when we did the iteration. And so this is our 133.27. This is our answer. So we've got the answers here, and as you saw, if we were not careful, we had the value of about 388 for our second root. So what I also did then was in Excel is nice for graphing things, and so I generated a graph of P versus V, and you can see this is what we have. This cubic equation of state is very unrealistic. And why is that? Because we actually go into negative pressures. All right. So that's another limitation of these cubic equations of state, why I don't like it, but this is actually what the Redlich-Kwong equation gives you. The real behavior will come down, and then it will have a straight, a horizontal tie line between here, and you will not, the reality is you will never have real pressures that are negative. So I'm using this example. This is kind of an odd example because the cubic equation gives you something that is not only unrealistic because it has three roots, but it's unrealistic because you can get negative pressures here, and that's just not right. Probably what we should have done is we should have added constraints that the pressure had to be positive value. So we could say, let me see, I'm doing this kind of on the fly here. So if we guessed 50, we could set the solver. Oops. Let's see if we can set the solver. We can say, we can add that the right-hand side has to be greater than or equal to, let's just say 1. And let's see if that gives us a better, that did not, solver could not find a point for which all constraints were satisfied. Well, anyway, that is, I guess you can say, let's resolve this. We get back our 133. That is another reason why I'm not a particularly big fan of using these cubic equations of state. But I think it's important that you at least see what these cubic equations do, how they work, and then how you can solve for the molar volumes. I would Personally, I would rather use the Excel solver than having to set up this iteration. Although once you set up an iterative scheme like this, it's good. So you know that whenever you need to solve for the saturated vapor or liquid volumes, you know, for the rest of your life, you can just copy and paste this for what it's worth. So we can do this. Here's an example of the Redlich-Kwong equation for where temperature is greater than the critical temperature. You can see our Redlich-Kwong isotherm doesn't have that dipsy doodle, and you're only going to get one molar volume. That's going to be for the vapor volume. Notice that the saturated liquid volume, if we do an iteration, it just blows up. It just up and down and bigger and bigger. It's never going to converge. We can't even get a number for the Racket equation as well. And so I've got a spreadsheet where I've got a bunch of these. Here's propane, I believe. You can see again the cubic equation is not realistic because it dips down into negative values. Here's one that's a little more realistic. This is for isobutane at these conditions. Again, temperature is less than Tc. So we will have 3 roots. You can just set up the equations. You can get the roots. I didn't solve for the middle root, but again, there are use the same solver routine to solve for this. All right, so that's Microsoft Excel Solver. There are tons of tutorials online. Just type in how to use Microsoft Excel Solver. I believe there will also even be some chemical engineering based with these cubic equations of state, maybe a simpler cubic equation like the van der Waals. I believe the Colorado State site has that. There's also one online where they have some grievous errors in the actual physical constants that they're putting in, but in the formulas, but they have, at least they show you how to use the solver right. But get used to using the solver for Microsoft Excel. It's going to be very useful for you. Next week, I will give you a take-home quiz problem where I will ask you to set up the Excel solver for one of these cubic equations of state. The other thing I wanted to point out is that doing the calculation with a second virial coefficient, the Pitzer correlation, is so much easier. That's why I like it. That's why I would encourage you to do this for yourself, especially on exams and quizzes where you have the freedom to use whatever you want to use. This calculation here is very easy. The Racket saturated liquid equation is also very easy. These are what I would encourage you to use on exams and quizzes when you can. The last thing I wanted to do is show you how to do this on with MathCad. And so I've got a MathCad worksheet here. I believe it's with the same, yeah, it's with the same problem with normal butane at these conditions. You have to enter the critical constants. And so we've got the critical constants. The values are given to you for these particular omega and psi. Then you calculate your reduced pressures, your reduced temperatures, and all the other Redlich-Kwong equation calculations that you have to do. Again, the nice thing about MathCad is it does all of the units for you, so I can put the units up here in anything I want, and as long as I have them nicely defined, everything is going to work out just fine in MathCad. And then we look at the solver function in MathCad. So again, you can go to the help menu for MathCad and get, there should be plenty of information of how to set this up. But the first thing that we have to do is we have to make a guess for the vapor root, all right? So what I've done is I've said, okay, for the saturated vapor, the best guess is an ideal gas, just like we did for Excel, all right? And so I guess Z is equal to 1, and then V, we calculate V from that first guess, just like that. So this is exactly what we did in Excel. Now here is the here's your little solver function in MathCad. You first type given. This is not text. This is a command. This is a MathCad command, given. So make sure you type it. If I type given like this and then put a space, that turns into text. Don't do that. So just type given. And then this is where I use my definition of the my defining equal sign. So this is Z control equal. Z control equal. This is my equation that MathCad is going to solve for. And then my vapor is going to be, given this first guess, my vapor, my Z value that it's going to solve for, I just type Z vapor. So that's what I want to calculate. This is going to be shift semicolon or shift colon, right? That gives me my assign equal function. And the solving function is called find Z. So this is my first guess of Z. This is my equation for Z. And then I'm going to say, okay, my real value, my calculated value is going to be find Z from this equation here. And that's what this is. So Z is equal to 0.83, so 83% of the ideal gas value. I calculate my new saturated vapor based on that, and I get the 2555.3 centimeters cubed per mole. I do the same thing for the liquid route. I type in, I make my guess, and remember that corresponds to a volume of about 80.6. I'm using the same equation, use the same find, and then this is my Z for the calculated liquid, and I get 133 centimeters cubed per mole. If I want to, I can make a guess for the middle route. And so the middle route, I did that, and I end up getting a value of 388. But this is just this is meaningless, right? This is meaningless. And I guess what I showed you here is that I don't even have to make this equation explicit in V, right? I made this equation just like we had before. That this equation is just written in terms of P as a function of V. MathCad can solve for that and give you that root. And then here we have the calculation in MathCad for the generalized correlation. You can see it's pretty fast. It's pretty fast, pretty easy, and I like doing it that way a lot better. If it were an ideal gas, we get this value. If it were saturated liquid, we get this value. You can see this is 115. What do we get with our Redlet Kwong? We got 133. You can see there's some difference there. All right, and we could look that up and we could see which one is closest. My guess is that the Racket equation might be a little bit more accurate. All right, so I will also give you a quiz where I give you the same kind of problem and ask you to solve for the molar volumes using the MathCad solver function. So that is a summary of 2 useful ways that you can solve for these things. Again, I think it's a good academic exercise for you to go through to figure out how to do this so you know what these cubic equations of state are dealing with, what their limitations are, how you deal with mathematical functions where there may be more than one solution, and you have to understand where you're starting from because that's going to have a strong effect on where you end up for that particular solution. It's not like very simple math problems where you've got one equation and you've got a very simple solution. We're now dealing with more complex functions that have multiple potential solutions for them. And as an engineer, you need to know how to set yourself up so that you're converging on the right solution, and how to check your answers to make sure you have that right solution.